In 1970, a group of Soviet engineers drove a drill into the ground on the Kola Peninsula in the far northwest of Russia, just past the Arctic Circle. They had a target in mind, 15,000 meters straight down, deeper than any instrument had ever gone. They were not looking for oil. They were not looking for anything they intended to extract. They simply wanted to know what was down there, what the inside of the Earth actually looked like, what it was made of. Geologists at the time had a confident model: granite for the first few kilometers, then a clean transition to basalt, the same layering seen on the surface of the moon. They expected the drill to confirm what they already believed they knew. They kept going for 24 years. And here's the number I want you to hold on to: 12.262 kilometers. That is how deep they got. That is the deepest hole any human being has ever drilled into the Earth. 12.262 kilometers straight down after 2.5 decades of drilling before the heat of the rock made the drill bits unworkable. The inner core of the Earth begins at roughly 5,150 kilometers below your feet. The Soviets reached 0.19% of the way there, not 1%, 0.19. And what they found on the way down, the water that shouldn't exist, the fossils, the gas, was strange enough to unsettle every assumption they'd brought to the surface. But I want to set that aside for a moment, because the real story I want to tell you starts with what's at the bottom. Not what we found drilling toward it, what that thing at the bottom has been doing, without our knowledge, without any instrument we could deploy to see it, for longer than complex life has existed on this planet. Here is what I want to tell you now, and then I want to take it back and earn it properly. Right now, 5,150 kilometers below where you're sitting, a ball of solid iron roughly the size of Pluto is spinning inside a sea of liquid metal. It is somewhere around 5,000 to 6,000 degrees Celsius, about as hot as the visible surface of the sun. It has been doing this continuously for hundreds of millions of years. You have never felt it stop. But in January of 2023, a pair of seismologists at Peking University published data suggesting that around the year 2009, it did something no one expected. I'll tell you what it did. But first, you need to understand something that should bother you more than it probably does. We have sent spacecraft to the edge of the solar system. We have mapped the surface of Mars in higher resolution than most of the Earth's ocean floor. We have decoded the human genome. We have split atoms and built machines that can hold plasma at temperatures hotter than the sun for fractions of a second. But we have never reached, seen, sampled, or directly detected anything about the core of our own planet. Not a single gram of material. Not a single direct measurement of temperature. Not a single photograph. Everything we know about the center of the Earth comes from earthquakes. That is the subject of this video. Not the science fiction version, the real one, which is stranger. The papers that sent me down this particular spiral are a pair from two independent research teams published about a year apart. The first is by Yi Yang and Xiaodong Song from Peking University, published in a journal called Nature Geoscience in January 2023. The second is by John Vidal, Ruoyan Wang, and their colleagues at USC, published in Nature in June 2024. And running alongside both of them, as critic, as context, as the voice that says not so fast, is a seismologist named Hrvoje Tkalčić, whose 2017 book, The Earth's Inner Core, Revealed by Observational Seismology, is the most comprehensive scientific account of everything we know and everything we don't about the thing at the center of the world. What makes this story unusual is not just the finding. It's the shape of the narrative. Two independent teams, different data sets, different methods, different continents, and a third scientist watching them both and saying, "You may be reading this wrong." That tension, the convergence, and the doubt running simultaneously is what makes this worth telling slowly. So let's go back to the beginning. Let's go back to the drill, the Kola Super Deep Borehole. They started in 1970. The drill site was on the Kola Peninsula, above the Arctic Circle, a landscape of pine and tundra and long winters. The goal was scientific: map the crust, confirm the model, prove what the interior of the planet looked like. Geologists expected the rock to transition from granite, the dense, ancient stuff that makes up most of the continental crust, to basalt at around 7 kilometers depth. That was the model. That was what everyone believed. They drilled. They pulled up cores of rock. They sent teams of scientists down borescopes to look at the walls of the hole. They kept meticulous records. And around the 7-kilometer mark, where the basalt was supposed to appear, it wasn't there. No basalt. Instead, more granite. Ancient granite, yes, but not what the model predicted. The first sign that the interior was stranger than the surface had suggested. They kept drilling. At around 6 kilometers, they found microfossils, single-celled organisms mineralized into the rock at a depth where the pressure and the absence of sunlight and the geological age of the formation should have made life impossible. Not impossible for life to exist there now, impossible for life to have been preserved there at all. Yet there they were. 24 distinct species of fossilized microscopic plankton buried in Precambrian rock, kilometers down. Nobody had expected that either. The deeper they went, the more unexpected things they found. The rock at those depths was fractured, not solid, as the models assumed, but cracked and porous, and it was saturated with water, not groundwater trickling down from the surface, mineralogically distinct water formed by geological processes at depth, water that had been there essentially forever, trapped under pressure in rock that was old enough to predate almost all complex life on Earth. The engineers described some of the material they pulled up as boiling with hydrogen gas. The rock around the borehole smelled of sulfur. There were temperatures approaching 180 degrees Celsius at maximum depth, hot enough that the drill machinery couldn't function reliably. After 24 years, they stopped at 12.262 kilometers. Now I want you to feel the scale of that number correctly, because the way we usually hear it, the deepest hole ever drilled, sounds impressive. It is impressive, but it doesn't convey the right thing. 12 kilometers sounds like a lot. It isn't. Put it this way. The radius of the Earth is 6,371 kilometers. The Kola borehole reached 12. If you shrank the Earth to the size of an apple, the deepest hole we have ever drilled would not break the skin. And the inner core, the thing at the center of the world, the thing I want to tell you about, begins at 5,150 kilometers down. The Kola engineers reached less than 0.25% of that depth, and the heat stopped them. We cannot go there. We cannot send a probe. We cannot take a sample. The pressures at the inner core boundary would crush any instrument ever designed. The temperatures would vaporize any material we could construct a vehicle from. There is no drill in any conceivable future that reaches 5,000 kilometers through rock and liquid iron. So how do we know anything about it? We listen to earthquakes. This is the part of the story that I find quietly extraordinary. Starting in the early 20th century, seismologists learned to read the interior of the Earth the way a doctor reads an X-ray, not by looking at it directly, but by sending waves through it and watching how those waves bend, slow, refract, and reflect as they pass through materials of different densities and states. When a large earthquake happens anywhere on Earth, it sends seismic waves rippling outward in all directions, including straight down through the planet's core and back up on the other side. Sensitive instruments on the surface, seismometers that can detect motion measured in fractions of a millimeter, record the arrival of those waves. And by comparing what arrived with what was expected, what was predicted by the physics of waves moving through different materials, geologists reverse engineer the properties of whatever the waves pass through. It is, as analogies go, like holding a flashlight against one side of a frosted window and trying to work out the exact shape and composition of the room on the other side purely from the shadows that reach you. Except the flashlight is an earthquake, the window is 6,000 kilometers of rock and iron, and your instruments are sensitive to motions smaller than the wavelength of visible light. The waves that actually penetrate the inner core are called PKIKP waves. The P stands for primary wave, the kind that compresses the material it travels through, alternately squeezing and stretching. The path these waves take is as deep as a wave can go. Surface, down through the mantle, through the liquid outer core, through the solid inner core at the planet's heart, and back up. PKIKP waves are the only instrument humanity has ever aimed at the center of the Earth. Everything we know about the inner core, its size, its temperature, its composition, its state of matter, and most importantly for our story, its rotation, is inferred from these waves. By the 1970s, seismologists had built up a reasonably confident picture. The inner core had a radius of roughly 1,220 kilometers, about the same as Pluto. It was made primarily of iron and nickel, with somewhere around 2 to 3% lighter elements mixed in, probably silicon or oxygen or sulfur or some combination, though the exact composition is still contested. And it was solid. That last fact is worth pausing on because it seems like it shouldn't be. Think about what I just told you. 5,000 to 6,000 degrees Celsius. That is comparable to the surface of the sun. At that temperature, iron is not just liquid, it's superheated plasma. So why is the inner core solid? The answer is pressure. At the boundary where the inner core meets the surrounding liquid, 5,150 kilometers down, the weight of everything above it presses down with a force of somewhere between 330 and 360 gigapascals. That is roughly 3.3 to 3.6 million times the pressure of the atmosphere at sea level. The pressure is so extreme that it raises the melting point of iron above the actual temperature. The iron wants to melt. The physics of heat demand that it melt, but the pressure won't let it. It's like trying to open a door while 5,000 kilometers of planet leans against the other side. The analogy that helps me is ice under a glacier. Near the base of a large glacier, the weight of the ice above can actually raise the melting point of the ice at the bottom, or lower it enough to keep it liquid as a lubricant, depending on the specific conditions. But the key principle is the same. Pressure changes what a material does at a given temperature. The inner core is the most extreme version of that principle anywhere on Earth. A ball of solid metal the size of a dwarf planet, sitting at the temperature of the sun's surface, kept from melting by the sheer weight of the planet surrounding it. Now, here is something the Standard Model did not predict. It spins, not with the Earth, on its own schedule. In 1996, a graduate student named Xiaodong Song, the same Xiaodong Song who would later be at the center of the 2023 paper, was working with a seismologist named Paul Richards at Columbia University. They were examining something specific, PKIKP wave travel times from earthquake pairs near the South Sandwich Islands, a remote archipelago in the South Atlantic Ocean recorded at seismometers in Alaska. Two locations roughly on opposite sides of the world, and they noticed something in the data. Over 30 years of earthquake records, the travel time of those waves, the time it took for the seismic signal to travel from the South Sandwich Islands down through the planet, through the inner core, and up to Alaska, had been changing, systematically, in one direction. The waves were arriving slightly later over time, by about 0.3 of a second over the course of those 3 decades, 0.3 of a second, in a journey that takes the wave about 18 minutes total. That is the precision of measurement I'm asking you to appreciate. Their interpretation, the inner core was rotating. Not with the rest of the planet, slightly faster. Because the inner core is seismically anisotropic, meaning that seismic waves travel through it at different speeds depending on the direction, about 3 to 4% faster along the rotation axis than across the equatorial plane. Any rotation of the inner core relative to the surface would cause a seismic path that had previously been sampling one alignment of the iron crystal lattice to start sampling a slightly different alignment. A different alignment means a different travel time, and a systematically changing travel time means rotation. Song and Richards estimated the rate at roughly 1 degree per year faster than the Earth's surface. That number has since been contested heavily. Subsequent studies with more data and more rigorous methods have substantially revised it downward. The actual rate, whatever it is probably a fraction of a degree per year. The exact figure is one of the central disputes in deep Earth geophysics, But the 1996 finding established something that has not been seriously challenged. The inner core does rotate at a different rate from the rest of the planet. Not locked to the mantle, not locked to the surface, spinning independently inside a liquid iron sea. Two gears of different sizes meshed, the smaller inner gear, the solid core, completing its turn at a fractionally different rate from the outer one. What Song and Richards found in 1996 was the millimeter-scale evidence that the gears were not perfectly synchronized. Now I need to tell you what happened to Xiaodong Song next, because this is where the story bends. He kept working for decades, and the dataset kept growing. More earthquakes, more doublet pairs, more decades of seismic records. An earthquake doublet is two earthquakes that happen at the same location on the same fault with the same mechanism. They produce nearly identical seismic waveforms. The technical term is repeating earthquakes. And when you have a pair of them separated by years or decades, you have something remarkably useful. The same signal sent twice through the same path at different times. Comparing the two isolates any change in what the waves pass through, not in the source. It's the seismic equivalent of running the same experiment twice with the same starting conditions and checking whether the result changed. By the early 2020s, Song and his then-student Yi Yang had accumulated enough earthquake doublet pairs from enough locations around the world to do something nobody had done before: build a global picture of inner core rotation across multiple decades. And when they did, they found something that the 1996 paper had not and could not have seen. The inner core had paused. In their 2023 paper in Nature Geoscience, Yang and Song reported that the systematic change in PKIKP travel times, the subtle drift that had persisted for decades, appeared to have stopped changing around the year 2009. Not just slowed, stopped changing globally, across earthquake pairs from multiple source locations and multiple recording stations. The signal that had been consistently accumulating for years had, around 2009, plateaued. The inner core's rotation relative to Earth's surface, the slow supersession of the gear, appeared to have paused. This is the point where the critical hedge has to come in, and I want to give it the space it deserves. Because this is where the science gets genuinely contested. What Yang and Song are measuring is not absolute rotation. They're measuring a change in travel time, which they interpret as a change in the angle at which the seismic path samples the inner core's anisotropic structure, which they interpret as a change in the inner core's rotational position relative to the mantle. That chain of interpretation, measurement to rotation, is sound in its logic, but contested in its specifics. One of the central critics is a seismologist named Tkalchich, whose 2017 book I mentioned at the start. He's not disputing the data. He's disputing what it means. One critique: Yang and Song used 31 earthquake doublet pairs in their analysis. Tkalchich, using a larger dataset, found that the implied oscillation period was not roughly 70 years as Yang and Song proposed, but something closer to 20 to 30 years. That's not a minor disagreement. A 70-year oscillation and a 20-year oscillation are very different physical processes. The answer depends critically on which earthquakes you include. A second critique, from a team led by Tian and colleagues in 2023, raised a more pointed methodological problem. When they added a third nearby seismic station to the Yang and Song analysis, the results implied that a patch on the inner core's surface would have moved east and west simultaneously, which is a geometric impossibility for a rotating sphere. That doesn't mean the rotation isn't happening, but it suggests the signal may be more complex than a simple rotation model captures. A third possible explanation, proposed by Liangxing Wen at Stony Brook University, is that the waveform changes don't require rotation at all. The inner core boundary, the surface where solid meets liquid at 5,150 kilometers down, is not a perfectly smooth sphere. It has topography, hills and valleys of solid iron varying by perhaps a kilometer. If that topography is growing and shifting over time, it could change the travel time of seismic waves without the core rotating at all. The debate is unresolved, the measurements are real, the interpretation is contested. But here's where it gets more complicated, because in June of 2024, a second team came to essentially the same conclusion. from a different dataset with a different method. John Vidale and Royan Wang at the University of Southern California compiled 143 pairs of repeating earthquakes from near the South Sandwich Islands, covering the period from 1991 to 2023. More pairs than any previous study of this kind, more decades of data, and when they ran their analysis, they found something that went a step further than yang and song. Not just a pause, a backtrack. Vidal's team found that the inner core had been super-rotating, spinning fractionally faster than the surface, up until somewhere around 2003 to 2008. Then it decelerated, and from around 2010 onward, it began sub-rotating, moving fractionally slower than the surface, not just pausing relative to the surface, falling behind it, retracing its rotational path, occupying positions relative to the mantle that it had previously occupied years earlier. Seismic paths that had changed one way, now changing back the other way. Vidal and his colleagues called it backtracking. The reason this matters scientifically, beyond the sheer weirdness of the idea, is that backtracking is harder to explain with boundary topography alone. For the boundary topography model to explain what Vidal found, the surface of the inner core would need to have grown and then retreated in precisely the same spatial pattern. That's not impossible, but it's much more specific and constrained than a simple rotation. The backtracking evidence, Vidal argued, is more consistent with the inner core having actually moved rotationally and then reversed direction. Yang and Song had proposed in 2023 that what they were seeing was part of a roughly 70-year oscillation. The inner core swings forward relative to the surface, reaches a turning point, swings back, reaches another turning point, swings forward again. A pendulum in slow motion. On their model, the previous turning point was somewhere around the early 1970s, and the next one would come around the middle of the 2040s. They estimated the amplitude at roughly 1 degree either side of the mean. Vidal's 2024 data independently confirmed that a turning point occurred around 2010. He didn't confirm the 70-year period. The dispute about that remains live. But two independent teams with independent datasets found the same feature at the same point in time. That convergence carries weight. Let me try to make the physical strangeness of this concrete, because the numbers, fractions of degrees, milliseconds, years, can make it feel abstract. What is actually happening if these results hold up? There's a ball of metal 5 times hotter than a furnace and wider than the United States is long, sitting at the center of the world, and it is spinning inside a sea of liquid iron. For decades, it was spinning slightly faster than the planet around it, like a gyroscope that's gained a little on its bearing. Then, around 2009 or 2010, it stopped gaining. Sometime around that same period, if Vidal is right, it began losing ground, rotating slightly slower than the planet, drifting backward relative to the surface. The planet did not notice. The length of day changed by somewhere between 1/100th and 1/10th of a millisecond. The tides didn't shift. The seasons weren't disrupted. The rocks of every continent continued doing what they've been doing for hundreds of millions of years. You were not aware of any of it. We only noticed because of a chain of earthquakes near a remote archipelago in the South Atlantic, the South Sandwich Islands, a string of volcanic peaks nobody lives on permanently, battered by the Southern Ocean, about as far from anywhere populated as geography allows. The earthquakes there, happening over decades, acted as a repeated signal, a clock ticking, and the seismic waves from those earthquakes arriving in Alaska showed a pattern that had changed. A millimeter precision tape measure laid across the planet, reading a number that changes by less than a second over 30 years. That is what we use to detect the rotation of a sun-hot ball of iron 5,000 kilometers underground. If that isn't the most delicate measurement in Earth science, I'm not sure what is. Now, I want to tell you something Vidal's team found that nobody had expected even as a secondary result, because it complicates the picture in a way I think is worth sitting with. When they ran their analysis across all 143 earthquake pairs, they found evidence that the outermost part of the inner core, the layer right at its surface at the boundary between solid and liquid, may not be simply rotating. It may be deforming. changing shape slightly over time, flowing in a way that solid material is not supposed to flow, at least not on the timescales we're talking about. The boundary between solid inner core and liquid outer core may be softer, more dynamic, more alive than the standard model assumed. Not a clean glass sphere rotating inside a liquid. Something stranger. Something in between states, where the extreme pressure and extreme temperature conspire to create a material that behaves in ways iron doesn't behave anywhere on the surface of the Earth or in any laboratory we've built. The image I keep coming back to is this. We assumed the inner core was a solid ball, a gyroscope, a well-defined object with clear edges spinning cleanly. What the data increasingly suggests is something more like a ball of iron that is simultaneously solid and barely solid, crystalline at its heart, but yielding at its surface, deforming over decades in ways that blend rotation and topographic change into something our models don't yet have clean language for. This is not a failure of science. It is science working correctly. The data outrunning the models, forcing a more complicated and more honest picture of the world. But it means the question is not simply, did the core stop and reverse? The question is, what exactly is an object like this? Does the concept of a rotation rate even cleanly apply to something that also deforms? Tkalčić, in his 2017 book, emphasizes this uncertainty with unusual care. He has spent his career mapping what the inner core is and what it isn't, and his conclusion, honest and a little humbling, is that the signals we're reading are real, but their interpretation is not settled. The inner core is there. It is solid. It is rotating at a different rate from the surface. Everything beyond that is subject to debate about magnitudes, mechanisms, and methods. He is not saying we're wrong. He is saying we should be more careful about what we claim to know. I think that honesty deserves its own moment, because we are not talking about a minor scientific uncertainty, a decimal place to be refined in the next study. We are talking about the fundamental engine at the center of the world, and the best answer current science can give is something is happening down there, and we're working out what it means. Hold on to that, because I want to tell you what that engine is actually running. You are alive right now, reading or listening to this, in an atmosphere. The air around you is roughly 21% oxygen, 78% nitrogen, trace amounts of everything else. It's been more or less like this for hundreds of millions of years, long enough for complex multicellular life to evolve, thrive, and eventually produce the particular arrangement of atoms that is you. Mars is a planet of almost exactly the same size as Earth. It formed from the same nebular disk. It has the same basic chemistry. It had liquid water on its surface for hundreds of millions of years. We know this from the rock record. And today, the Martian atmosphere is about 1% of Earth's, so thin it would kill you in seconds. The surface is bombarded by ultraviolet radiation and ionizing particles from the sun. The water is gone. What happened? Mars lost its magnetic field, Earth's magnetic field, the invisible force that makes compass needles point north, that protects the ISS crew from radiation storms, that bends the solar wind around our planet rather than letting it hit us directly, is generated by the same liquid iron I've been describing, the outer core. The churning sea of liquid iron that surrounds the solid inner core, from about 2,890 kilometers down to 5,150 kilometers. Liquid iron in constant motion, driven by heat escaping from the interior and by the buoyancy of lighter material rising as iron crystallizes at the inner core boundary. That convection, organized into helical columns by the Coriolis effect of the Earth's rotation, moves conductive iron through space. Moving conductive iron generates electric currents. Electric currents generate magnetic fields. Those magnetic fields, in turn, organize the convection that drives them. The whole system is self-sustaining, not a perpetual motion machine, because it runs on the genuine fuel of Earth's internal heat, but something that looks like one from the outside, a geodynamo that has been running for billions of years. And the result, the product of all that churning iron, all that liquid metal in motion, is a magnetic field that extends 65,000 kilometers into space on the sunward side, and much further on the night side. an invisible bubble surrounding the entire planet. The solar wind, a continuous stream of charged particles blasting outward from the sun at several hundred kilometers per second, hits that bubble and deflects around it. Some of it leaks in at the poles, spiraling down magnetic field lines and creating the auroras. But most of it misses us entirely, because the iron is moving. On Mars, the geodynamo stopped, probably because the planet's smaller size meant its interior cooled faster, too fast for the liquid iron convection to sustain itself. And once the dynamo stopped, the solar wind had nothing to push against. Over millions of years, it gradually stripped away the upper atmosphere. The water went with it. The surface became what we see today. The atmosphere you are breathing right now exists in part because of the iron churning at the center of the Earth. I want to let that actually land. This is not a metaphor. The oxygen in your lungs was produced by life. Yes, by billions of years of photosynthesis, but the atmosphere that keeps that oxygen from bleeding off into space, the magnetic shield that prevents the solar wind from stripping away the upper layers layer by layer over geological time, that shield is a product of the geodynamo. The geodynamo runs on convection in the liquid outer core, and the inner core, the solid ball at the center, rotating on its own schedule, apparently pausing and reversing over multi-decade cycles, is not separate from that process. The inner core boundary is where iron crystallizes, releasing latent heat and lighter elements that drive the convection. The inner core is the heart of the geodynamo in a literal sense. It is the source of the buoyancy that keeps the outer core in motion. The precise relationship between inner core rotation and the magnetic field is one of the genuinely open questions. There are correlations in the data. Periods when the inner core appears to have been rotating in one direction seem to correlate with changes in the length of day and possibly with longer-term variations in the magnetic field's strength and structure. But correlation is not mechanism. Whether inner core oscillation directly influences the geodynamo, or whether both are driven by a shared, deeper process, or whether they're largely independent phenomena that happen to correlate, that is not settled. What is settled is this: the inner core and the geodynamo are part of the same system. You cannot separate them. The solid ball at the center and the liquid ocean surrounding it are one interlinked machine. The machine has been running since before there was life on this planet, and right now, the machine appears to be doing something that surprised the scientists who spend their careers listening for it. Let me come at this from a different angle, because I think there's something important hiding in the way we discovered all of this. Every single thing I've told you about the inner core, its size, its temperature, its composition, its rotation, its oscillation, was inferred from signals that never touched it. PKIKP waves propagate through the inner core, yes, but they don't carry a sample back to the surface. They arrive as a tiny vibration in a seismometer, a needle swinging in a very precise instrument bolted to rock somewhere on the Earth's surface. Everything is interpretation. Everything is a calculation. The model of the inner core, the standard picture, the one that says it's roughly 1,220 kilometers in radius, made of iron and nickel, kept solid by pressure, rotating differentially, that model is a best fit to the shadows that earthquake waves cast through it. The shadows are measured. The object casting them is inferred. In a sense, we have never directly detected the inner core at all. We have detected its absence, the shape of the gap it carves in the seismic data. We know it's there the way you might know there's a fish in a lake you've never seen, because something keeps disturbing the water in a way that has a particular pattern. This is not a weakness of seismology. It is an almost philosophical fact about the limits of knowledge. The center of our own planet is more inaccessible to direct observation than the surface of distant stars. We can measure the spectra of stars light years away more precisely than we can directly probe the material 5,000 kilometers straight down. We have pointed enormous telescopes at galaxies a billion light years distant and taken detailed images of their structure. We have built instruments sensitive enough to detect gravitational waves from colliding black holes a billion light years away, ripples in space-time with amplitudes smaller than a proton. But the iron at the center of the Earth? We listen for it, we infer it, we argue about what the shadows mean. And we are still arguing. This, I think, is where the science becomes genuinely beautiful. Because the argument is not happening because scientists are confused or incompetent. It's happening because the data is at the absolute edge of what our instruments can resolve. A difference of fractions of a millisecond in a wave travel time across decades of earthquake records, that's the signal. Noise in the data, uncertainties in earthquake locations, variations in the mantle that the waves also pass through on their way in and out. Any of these could introduce artifacts. The scientists critiquing Yang and Song and Vidal are not doing it from ignorance. They're doing it from exactly the same rigorous attention to what the data actually supports versus what we'd like it to mean. Tkalchich, Tian, and colleagues, Wen. These are not contrarians. They are scientists doing what science is supposed to do, demanding that the evidence match the claim before the claim is accepted. What we can say with confidence as of the middle of 2024 is this. The inner core rotates at a different rate from Earth's surface and mantle. That is established. The differential rotation is small, fractions of a degree per year, not the roughly 1 degree per year Song and Richards originally estimated in 1996. Two independent teams using different earthquake datasets and different methods found evidence that the inner core's rotation relative to the surface changed around 2009 to 2010, and that Vidal's team specifically found evidence of backtracking, the core reoccupying positions it had previously held. The disagreements are about the precise period of the oscillation, the amplitude, and whether some or all of the signal could be explained by inner core boundary topography rather than rotation. The 2040s are when, on Yang and Song's model, the next turning point would come. If it comes. If the proposed 70-year cycle holds, and if the oscillation is real, then in the 2040s, seismologists will be watching their earthquake doublet data very carefully for the moment the inner core shifts direction again. It would be the first predicted turning point in Earth's inner core rotation in history. Not a prediction of earthquake or catastrophe, nothing you would feel, but a confirmation or a refutation of the model. I find myself thinking about the scientists who will be doing that watching, the ones who are probably graduate students right now, learning seismology, reading these papers, working out the methods. They'll be in their 40s when the next turning point is supposed to arrive. They'll have spent 2 decades preparing to interpret a signal that arrives as a fraction of a millisecond shift in a seismometer reading from the South Sandwich Islands. And they will either see the pattern continue or they'll see something that forces the entire model to be revised. That is how science moves at the edge of what's knowable. Slowly, carefully, across careers and decades. There's something else I want to draw out of the mechanism, something that doesn't get said enough. We have talked about the inner core as the subject of this story, the thing that's doing something unexpected. But the inner core is not the protagonist in the sense that matters most for your life. The geodynamo is the protagonist, and the geodynamo is not a machine you can afford to stop noticing. The magnetosphere, the region of space controlled by Earth's magnetic field, extends roughly 65,000 kilometers toward the Sun. On the night side, it stretches much further, pulled into a long tail by the solar wind. Everything within that region is, in a fundamental sense, protected. The solar wind carries charged particles, protons, electrons, heavier ions, blasting outward from the Sun at speeds of around 400 to 800 kilometers per second under normal conditions and much faster during solar flares and coronal mass ejections. Without the magnetosphere, those particles would bombard the upper atmosphere directly. Over geological time, they would sputter it away, the same process that stripped Mars. Over shorter timescales, intense solar events would cause radiation doses at ground level severe enough to be dangerous to complex life. The magnetosphere has weakened and strengthened over Earth's history, and the magnetic poles have reversed hundreds of times. The geological record in magnetized rock shows this clearly. During polarity reversals, the field doesn't disappear, but it weakens, sometimes substantially, for periods of thousands of years and becomes less organized. There's evidence this has happened without causing mass extinctions, though the record is complicated. But the field has never disappeared completely, as far as the record shows, for as long as complex life has existed. It has always recovered. The reason it recovers is the same reason it exists. The liquid outer core keeps churning. The heat from the inner core boundary keeps rising. The Coriolis effect keeps organizing the convection into helical columns. The dynamo keeps sustaining itself. This is the engine beneath everything, invisible, inferred from shadows, hot enough to vaporize any material we've ever made, running without interruption for longer than animals have had eyes. Here is something I think about more often than I should. The magnetic field protecting you right now is invisible. You have never seen it, felt it, or heard it. Without a compass, you would have no sensory evidence it exists at all. The auroras are its only visible symptom. Curtains of light at the poles where the field's geometry funnels solar particles down into the atmosphere. If you've never seen an aurora, you have no first-hand evidence of the field's existence. You take its existence on trust because the physics is well understood and the compass needle moves and the GPS satellites account for it in their calculations. The liquid outer core that generates it is equally invisible. More so. At least the magnetic field has measurable effects at the surface. The liquid iron, 2,600 kilometers of it, churning in the dark, has no surface expression at all. It generates heat, yes, some of which eventually reaches the surface. It drives the geodynamo, but you feel none of it. You cannot point to a mountain range and say, that's the outer core working. The effects are global, diffuse, and ancient beyond any individual's frame of reference. And the inner core, the solid ball at the center, the one whose rotation rate appears to have paused and reversed, you have even less connection to that. 70 years is the proposed period of its oscillation, one full swing in 70 years. That is roughly a human lifetime. The cycle apparently reached a turning point around the early 1970s, according to Yang and Song's model. It reached another turning point around 2009 or 2010, confirmed independently by two research teams. The next one is predicted for roughly the middle of the 2040s. Think about that in human terms. People were born, grew up, lived entire adult lives, and died between the last two turning points. The inner core completed half a swing of its oscillation while the 20th century played out, while satellites were launched and the internet was built, and the human population doubled, and the Antarctic ice cores were drilled, and the Kola borehole reached its maximum depth and was abandoned. None of those people knew the clock was ticking. The seismological tools to detect it barely existed for most of that time. The specific earthquake doublet analysis that revealed it didn't exist at all. We are the first generation of human beings who know this is happening. That is a sentence I don't want to say too quickly, not as a headline. As an actual fact with weight behind it, every human who has ever lived, for all of recorded history and for all of the 300,000 years of anatomically modern Homo sapiens before that, stood on the surface of a planet whose inner core was oscillating through a 70-year cycle, probably, we don't know the period with certainty, and had no idea. The cycle was invisible. The engine was running. Nobody noticed. We noticed in 2023. Because a seismologist named Xiaodong Song spent decades accumulating earthquake doublet pairs, and because the South Sandwich Islands happened to produce enough seismicity across enough decades to build a clean statistical signal, and because the waves from those earthquakes happened to pass through the inner core at an angle that makes rotation detectable. If the South Sandwich Islands were seismically quiet, we might not know yet. I want to stay with the scale of deep time for a moment because the inner core's oscillation is just one layer of its history, and the full history is more staggering than the recent behavior. Let me tell you something that is genuinely contested. I want to flag that clearly, but is worth understanding. The inner core is not as old as the Earth. The Earth formed about 4.5 billion years ago, condensing from the solar nebula, heated by the energy of accretion and by radioactive decay. For much of its early history, it was probably entirely or mostly molten, a magma ocean, cooling over hundreds of millions of years. The inner core, the solid ball at the center, formed later. As the Earth cooled, the pressure at the center eventually became high enough relative to the local temperature and iron's melting curve for solid iron to begin crystallizing out of the liquid. The inner core started growing. When did this start? This is contested. Estimates in the literature range from about 500 million years ago to about 1.5 billion years ago. That is not a small range. The difference between those extremes is a billion years. The uncertainty comes from the difficulty of constraining the temperature history of the deep interior, which depends on assumptions about heat sources, cooling rates, and the properties of iron alloys under core conditions, all of which are themselves subjects of ongoing research and debate. But here is what that range tells you. Complex multicellular animal life, the kind of life that leads eventually to fish and amphibians and dinosaurs and mammals, did not appear until roughly 600 million years ago, at the earliest. Depending on which estimate for the inner core's age you use, the solid inner core either predates complex animal life by nearly a billion years, or it grew into existence around the same time complex life was beginning. The Cambrian explosion, the sudden diversification of animal body plans, the event that gave rise to almost all the major animal groups alive today, happened about 530 million years ago. It is possible that the inner core was still young when the first animal eyes opened. It is possible that the solid center of the Earth is only as old as the animal kingdom. We don't know. The exact age is one of the genuinely open questions in deep Earth science. What we do know is that the inner core is growing right now, slowly, incredibly slowly, by maybe a millimeter per year at the boundary, though this figure is also uncertain. Iron is crystallizing out of the liquid outer core and attaching to the solid inner core's surface. The solid sphere at the center of the Earth is larger today than it was when you were born. The heat and the lighter elements released by that crystallization are part of what drives the convection in the liquid outer core, which drives the geodynamo, which generates the magnetic field that is protecting the atmosphere you're breathing. The inner core is not ancient and fixed. It is alive in the geological sense, growing, changing, oscillating, crystallizing, possibly deforming at its surface. It is a process, not an object. And it has been running, uninterrupted, unseen beneath every human life ever lived. Now I want to do something slightly unusual and walk you through the measurement one more time. Not the findings, but the act of measurement itself, because I think there is something in it that gets lost when we move too quickly to the conclusion. Imagine you are a seismologist. It is sometime in the early 1990s. You have access to seismometer data from a network of stations distributed around the globe. You are studying repeating earthquakes near the South Sandwich Islands, a pair of events that happened years apart at the same fault, producing nearly identical waveforms. You have the seismogram from the first event and the seismogram from the second. You overlay them. They are almost the same, but not quite. The waves that traveled through the inner core, the PKIKP arrivals, are shifted slightly, a fraction of a millisecond. The wave took slightly longer to arrive the second time, or slightly shorter, depending on the geometry. You know the earthquake locations. You know the receiver locations. You've corrected for everything you can think of. The structure of the mantle, the velocity of the wave in the outer core, the clock accuracy of your instruments. After all those corrections, the residual shift is still there. And it points in a direction that is consistent with the inner core having rotated slightly between the two events, a fraction of a millisecond, across a journey that takes roughly 18 minutes. The signal you are trying to detect is about 1 part in 4 million of the total travel time. Now multiply this by decades, more doublet pairs, more years, more stations, to build up a statistical picture across 30 years of data, and the pattern emerges. The travel time has been changing systematically. The inner core has been moving. Then keep going. Add more decades. The change that was accumulating over 30 years appears to stop around 2009. The systematic drift plateaus. And then, in Vidal's analysis, with 143 pairs spanning 1991 to 2023, the drift reverses. All of this from a needle swinging in a seismometer. All of it from the shadow of an earthquake wave passing through a ball of iron 5,000 kilometers below the South Atlantic Ocean. I find this beautiful in a way that I struggle to articulate clearly. It is not just that the measurement is clever. It is that the measurement required time, decades of it. You couldn't rush this experiment. You couldn't design a lab to do it faster. The only way to detect a multi-decade oscillation is to wait out the decades and keep listening. The scientists who are interpreting this data now are building on records started by people who are retired or dead, using instruments installed before many of the current researchers were born. Science, at its deepest, is a multi-generational project, and nowhere is that more literal than here, where the phenomenon itself unfolds on the scale of human lifetimes. Let me come at the question of what we don't know from a different direction, because the honest limits of this story are as interesting as the findings. The composition of the inner core is unknown at the level that matters most. We know it's mostly iron. We know it's partly nickel. We know there are lighter elements, somewhere around 2 to 3% by some estimates. But whether those lighter elements are primarily silicon or oxygen or sulfur or some combination, that is contested. The answer matters because different compositions imply different thermal conductivities, different viscosities at the inner core boundary, different behavior under the extreme pressures involved. The composition affects the cooling rate, which affects the age, which affects the history of the geodynamo, which affects how the magnetic field evolved over geological time. We also don't know whether the magnetic field has always been strong enough to protect the atmosphere. There are periods in the geological record, identified from the magnetic signatures of ancient rocks, when the field weakened substantially. Whether those weakening periods coincided with atmospheric changes, or changes in ocean chemistry, or mass extinctions, is an active area of research. The links are suggestive, but not cleanly established, and we don't know whether the proposed oscillation will behave as predicted. The 70-year period is a model fit to about 50 to 60 years of seismic data, barely one full oscillation. Extrapolating from one cycle to predict the next is not the same as understanding the mechanism. If the period is actually 20 to 30 years, as Tkalchit's analysis suggests, then the prediction is wrong, and the next turning point should already be approaching or may have already passed. The difference between a 20-year and a 70-year cycle is not a detail. It's a fundamentally different physical process. What would resolve this? More data, more decades of earthquake doublet records, better coverage of the globe with sensitive seismometers, better models of mantle heterogeneity, so that variation in the mantle can be cleanly separated from variation in the inner core signal. And, eventually, though this is decades away at minimum, better constraints on the inner core boundary topography so that the "it's not rotation, it's topography" alternative can be more rigorously tested. The people who will resolve this are probably not yet working in research. They're undergraduates right now, or high school students. They'll inherit the question and the data and the dispute, and they'll add their own decades of earthquake records to the archive, and eventually the picture will sharpen. That is the actual pace of discovery at the frontier. And I want to make sure you feel what that means for right now, not in the future. Now. Right now, beneath your feet, not metaphorically, literally, directly below where you are sitting or standing, the following things are happening simultaneously. At around 30 to 50 kilometers down, depending on whether you're on a continent or an ocean floor, the crust gives way to the mantle. The mantle is not liquid, but it flows on geological timescales, slowly over millions of years, driven by the temperature difference between the hot interior and the cooler surface. This is what drives plate tectonics, the slow churning of rock you cannot feel. At about 2,890 kilometers down, the mantle gives way to the liquid outer core. The temperature jumps. The material changes from silicate rock to liquid iron-nickel alloy. Convection here is much faster than in the mantle. The liquid is turbulent, driven by heat and compositional buoyancy, organized by the Coriolis effect into structures that are still being actively modeled. At 5,150 kilometers, the liquid outer core gives way to the solid inner core. The pressure there is 330 to 360 gigapascals. The temperature is somewhere between 5,000 and 6,000 degrees Celsius, comparable to the visible surface of the sun. The iron is solid because the pressure has raised its melting point above the actual temperature. And that solid ball, roughly 1,220 kilometers in radius, the size of Pluto, is rotating, perhaps slightly faster than the planet around it, perhaps slightly slower, perhaps right now at a turning point, perhaps partway through a 70-year swing or a 20-year swing or something else entirely. And at its surface, iron is crystallizing out of the surrounding liquid at a rate of perhaps 1 millimeter per year, releasing heat and lighter elements that drive the convection that runs the geodynamo that generates the magnetic field that is, right now, deflecting the solar wind 65,000 kilometers above your head. All of this is happening, continuously, below you, right now. You are sitting on top of an engine you can't see, can't reach, can't directly measure, and have only just begun to understand. The engine has been running for longer than animals have existed. The fact that the surface of that engine is mostly quiet enough for cities and farms and roads and everything built on it. The fact that the convulsions of that interior mostly manifest at the surface as earthquakes and volcanoes rather than something catastrophic enough to sterilize the planet is itself a kind of geological fortune. And that fortune has held for billions of years. In 1994, the Soviet engineers on the Kola Peninsula switched off their drill for the last time. They capped the borehole. They left the equipment to rust in the Arctic wind. The hole is still there, a small metal cap on a concrete pad in the tundra, unremarkable from a distance, the deepest wound humanity has ever made in its own planet. 12.262 kilometers, 0.19% of the way to the inner core. They didn't reach it. They were stopped by heat. I keep coming back to that image, not because it's a failure. It isn't. It's one of the most extraordinary scientific projects ever attempted, but because of what it tells you about the nature of the thing we're trying to understand. The rock became too hot to drill through at 12 kilometers. The inner core begins at 5,150. There is no conceivable drill. There is no instrument. There is no path. Every fact we have about the center of the world arrived as a shadow cast through earthquake waves, read by seismometers, interpreted by scientists sitting at desks on the surface of a planet they cannot fully see into. And from that, from those shadows, those fractions of milliseconds, those decades of careful listening, they pulled out this, a sun-hot ball of iron the size of Pluto, spinning on its own schedule, apparently pausing and reversing direction on a cycle longer than most human lives, driving the invisible magnetic field that keeps the atmosphere on this planet, the water that shouldn't have existed at 6 kilometers down, the fossils where no fossils should be, the mud boiling with hydrogen. The Kola engineers found a world under their feet that was stranger than the model they brought with them, and they only scratched the surface, literally, by a fraction of a percent. What I take from all of this, from the Yang and Song paper, from Vidale's backtracking data, from Tkalchic's careful insistence that we be honest about what the shadows actually tell us, is not dread. Or not only dread. It's something closer to a recalibration. A reminder that the ground beneath you is not the bottom of anything. It is a thin shell over a system so extreme and so active and so old that we are still, right now, in the early stages of understanding it. The engine is running. It has always been running. You have never felt it. But the air you're breathing exists because it hasn't stopped. Somewhere 5,000 kilometers below you, iron is crystallizing. Liquid metal is rising in helical columns, churning in the dark, sustaining a magnetic field that extends 65,000 kilometers into space. And at the very center, a solid ball the size of a world, hotter than the surface of the sun, kept solid by pressure that makes the atmosphere feel like nothing, is turning. On its own time, to its own rhythm. A rhythm that takes longer than a human life to complete one swing. We noticed it changing in 2023. We don't fully know why it changed. We cannot go look. The deepest we ever got was 12 kilometers. The heat stopped us. The heat, it turns out, was just the beginning.